So hi, welcome to Make or Repair. This is a dummy loudspeaker that I was meaning to make for a long time and finally got round to, and of course I knocked it together out of a lot of parts that I had in my lab. The only thing I bought for it were the resistors inside. This switches between 4 and 8 ohms, it's stereo, and essentially just replaces the loudspeakers when we're testing amplifiers and things like that. And of course it's essentially a perfect load, so we really get to test the amplifier output and not the behaviour of the amplifier joined to real world speakers. So we can test its total harmonic distortion, and we can test its signal to noise ratio and things like that, and the flatness of its frequency response without having to worry about the impact of real loudspeakers. So that's all great. This does have an attenuation output as well, and this is so that I can join it safely onto my audio analyzer. So my audio analyzer is a Quantasylum analyzer. It's a QA403. And that enables me to look in some detail at the quality of what's coming out of the amplifier, and indeed to apply signals into the amplifier and test the amplification, the gain and things like that, the flatness of the gain, etc. This works okay. It kind of works as I intended, but once I'd built it and used it, I realised I kind of hadn't paid enough attention to the detail. I'd focused too much on the attenuation and the load and things like that, and not enough attention to the detail. So what I'll do is I'll show you the circuit diagram for this. I'll look at the theoretical attenuations here, and then we'll run a few little tests on it and see how it stacks up in real life and where I feel that I could have actually done better. And then I'll show you the design that I've put together, which will enable me to hopefully overcome the weaknesses of this. And it may surprise you to see that something as simple as a bunch of resistors can really have some weakness. So here we go. Let's quickly draw out the circuit diagram for this. So we've got a resistor here which is 4 ohms. And then we have our, what I'm going to call our sense resistor, which is a 0.1 ohm resistor. And then we've got another 4 ohm resistor just here. And this is our plus and minus loudspeaker connections. So that comes up to 8.1 ohms in total across here. Now our attenuated signal we take from just here. Like that. So that's it, we've got an 8 ohm. Now to turn this into 4 ohms, what we have for each of these 4 ohm resistors, we have another 4 ohms that's ready to go in series. Like that. So we switch the 4 ohms in, and each of these becomes a parallel pair. 2 4 ohms in parallel is 2 ohms, so this now becomes a 4 ohm loudspeaker with an error of 0.1 ohms. Now, I'm not too worried about that 0.1 ohms because truthfully, you know, we could make this 10 ohms or we could make it, you know, anything we like, as long as we're in the ballpark of the impedance for the speaker. When we start looking at dB volts and watts and things like that, then we can do our wattage calculations. We're going to measure dB volts. We can do our wattage calculations using a true 8.1 ohm or whatever we actually measure this to be, because to calibrate this we're going to want to measure the true resistances that we actually have in place between the two speaker terminals. We're also going to want to measure the difference between an input here and the output here, so we actually get some calibration data. For our dB, which is a dB volts, we're going to do 20 times the log, which is to base 10, of 0.1, which is this resistor, because we want a ratio between this resistor and the total resistance. So let's say 8.1. So that's our log for our 8 ohms, and 20 times log, that's our dB. So that's our dB volts for our 8 ohms, and for our 4 ohms it'll be 0.1 over 4.1. And that's theoretical, of course. So let's quickly do those. So that's minus 38.17 dB volts. and this one should be about minus 32.26 dB volts. And actually, that straight away is one of the weaknesses of this circuit, which is that at the two different impedances we get two different attenuations. Now, since I've got two channels, we could also end up with quite a big mismatch between the two channels. So to do that, now I need to get 8 of these and actually measure them very, very accurately with a 4-wire resistance measurement on a 6-digit multimeter, and then I can pair them up so that the differences between the two dummy loudspeakers are essentially irrelevant. They become tiny and ignorable. So that's it. It's a fairly simple schematic, fairly simple circuit, and it looks like it will, in terms of being a dummy load, it's of course going to work absolutely fine. In terms of being an attenuator, that seems to be pretty reasonable. Bit of a downside that we've got different attenuations at different impedances. That's a bit of a shame, and I should have thought about that when I built this, because of course I'm recording this after I built it and tested it. In terms of the heat, we need a big heat sink. So actually this is going to be cut in half, and half the resistors on one and half the resistors on the other. And if it starts getting too hot, then I can of course put a fan in it to assist things, but one step at a time, I think. So why is this resistor, by the way, in the middle? Well, it's in the middle because, let me just sort of simply draw this out here. So supposing that I'd taken my dummy here, my sense resistor here. Now on some amplifiers what we have is we have an amplifier up here and this is ground. And that's absolutely fine, isn't it? Because all the attenuation happens through these two resistors, and we get a ground referenced nice little signal coming out here versus the huge signal that's going in here, this one being DC. So that's absolutely fine, it works perfectly, not a problem at all. What happens though, if we have complementary signals, so this one's going up and down like that, and this one's going down and up like that. What happens now, of course, is that we have this entire full signal. So this might be moving, let's say 15 volts. We've got that entire signal on the output, and then we've got the difference between these two signals attenuated by a resistor on here. So we've still got a small signal on here, but that small signal is superimposed on this signal essentially. So we have what's called a huge common mode signal coming through to our amplifier. So that's going to come through to our input amplifier on our analyzer or our oscilloscope or whatever it is that we're using. And that's not good news, because the signal we're interested in is a tiny percentage of the total signal that we're receiving on the two. Now in theory, if this is a perfect operational amplifier on the input to the analyzer, then the common mode signal will be entirely cancelled out, because this is a positive input, this is a negative input. Even if it has transistors at the start, they're essentially going to make some form of difference amplifier like this. And this is called common mode rejection ratio. I'm not going to go into it in huge detail here, except to say it's going to be almost impossible to remove that in a real device. It's going to be almost impossible to remove that common mode signal that's on there, because in theory it should all vanish and we should just be left with the difference. In practice, there are minor differences between these two amplification channels, if you like, and it's not going to cancel out totally. So we will have our actual signal under test that we want to look at will be occluded within a bigger common mode rejection or common mode signal. So that's why we move up to here. So we don't put that there. We move up to here, and now essentially we've got our big signals coming in here. They are both attenuated against each other through this little resistor in the middle, and so pretty much our common mode is pretty much removed by the positioning of this resistor. Now it's not going to be perfect because there will be a tolerance between these 2 points, but it will be almost entirely removed, and we can easily handle the common mode rejection ratio in our amplifier. So that's why that's in the middle, not on the bottom. And of course, if this is DC, that still works perfectly well. It just has an offset. But of course, since the first step on the input to our analyzer is going to be a capacitor, we don't care. So we're connected up, ready to make some measurements. I've got my audio analyzer over here. I've got my amplifier here. Now, coming out of my audio analyzer are two identical signals going to the CD input of this. And they're set at minus 14 dB volts, which is kind of round about 200 millivolts RMS, which is kind of fine for the input to a CD input or line input. So those are there, and I'm running them at 3 kilohertz, so they're easy to find on the screen when we look at the analysis that's happening behind us. This in turn is outputting through these two speaker cables and into the dummy load. The dummy load is set to 8 ohms, and that's because this is specified for 6 ohms or greater in terms of impedance for the loudspeakers. In truth, it's not going to blow up if we put it into 4 ohms, but it could start clipping and doing a few awkward things. We will run it on 4 ohms just to see some differences. Okay, so what else have we got going on? Well, I've got my attenuated output from here. It's coming through here and it's going into the left-hand channel on the analyzer, and the left-hand channel is yellow on the screen, and I will switch across to the screen in a second. You can see it behind me. So that's the attenuated, and for the time being I also have something connected directly across the loudspeakers. So I'm just making sure that I don't use too much power coming out of this going into the analyzer. I need to make sure I'm attenuating sensibly at the analyzer for whatever level I have got. So I'm monitoring the loudspeakers, which is something I wouldn't normally want to do. I'm monitoring the attenuated, and I'm going to display them both on the screen for you. So let's switch across to the screen. So if we look across the top, we can see the left peak dB volts, and over here the right peak dB volts. So if you remember, left is attenuated, that's the yellow, and right, which is red, is non-attenuated. So those are our two signals, and I've adjusted the amplifier so that the output is close to 0 dB volts, because that's easy to do maths with, really. So if we look on the display, we can see that there's a red line coming all the way up to 0, and the yellow line that's coming to minus, well, 38, 39, 40 just here. So that's our attenuation. What I really need to do is, of course, is to fine tune this now so that I get 0 dB volts for the right hand channel, and then I'll be able to just read off the attenuation from the top left here. So how do I do that? Well, unfortunately I can't just turn the volume knob on my amplifier because it's a digital knob and its steps are too big. So what I can do instead is I can change the generated signal, and I can reduce it by 0.04 dB volts. 0.04 I think it was. There we go. So minus 14.04 gives us 0 dB volts. And we can see our input is minus 37.99. So if we look at my little diagram from earlier, we can see I estimated it to be minus 38.17. So my attenuation is actually fractionally below that, but it's not bad. Okay, so there's my right power again at 0. And looking now, we've got minus 32.89. Now, my estimate for that was, or perfect condition for that was minus 32.26. So minus 32.89, not far off. I'm pretty close to the ideal calculated amounts. Okay, so I'm going to measure the right hand side as well, do both 4 and 8 ohms, and then I'm going to heat this up with maybe 400 watts of power for half an hour or so, and then we're going to remeasure the attenuations to see how thermally dependent they are, and then I'll put the results on the screen. So here we go. We can see there's not too much difference between left and right channel, but thermal behaviour not too good. If we look at the 8 ohm up at the top left there, we can see cold it's 38.12, minus 38.12, and yeah, when it's hot it's minus 37.28, so that's nearly 1 dB volt difference in the attenuation. And I only heated this up till it was kind of uncomfortable to touch. I didn't really kind of give it the equivalent of a soak test, and it got hot faster than I would have hoped. what can we see on this graph here then? So I've still got my two channels connected up. So the red is the loudspeaker, the raw loudspeaker signal, and the yellow is the attenuated signal. And it looks like the same signal, doesn't it? Just lower, of course, which is what you'd expect. Only there's a problem. The noise floor of the quantum analyzer is about minus 140 dB, which is really, really good, by the way. But if we look at this yellow, we can see the noise is at minus 140 dB, thereabouts, apart from on the left, where it's peaking up a little bit. This is actually harmonics rather than noise, but you know, same difference, it's interference, I guess. If we look at the red, it's the same pattern, only set up higher. So the noise floor for the right hand side is still minus 140 dB. So what we're looking at here is a real noise signal. This is the noise from the amplifier versus its input. So we can calculate a signal to noise ratio from that, which is going to be about minus 90 dB thereabouts. Apart from on the left hand side here, where it gets a lot worse and goes to 75 dB. So what's happening then on my attenuated signal? Well, my attenuated signal is 40 dBs down. So when I take this noise here, subtract 40 dBs of it, it just vanishes into the noise floor of the analyzer, which means I can't measure the signal to noise ratio of the amplifier using. So up at the right hand side here, we can see that the red side, which is measuring the speaker directly, thinks the signal to noise ratio is 75 dB, thereabouts. And the left hand side, where the noise has vanished into the noise floor of the instrument, is measuring it at 73.2. So we're a couple of dBs off on the noise measurement because we're not really measuring the noise of the amplifier anymore. I mean, we are to some degree, because we know that this red noise has vanished into the noise floor of the instrument because we can see these harmonics still poking their head out on the left hand side, although they're not poking their head up quite as much as they should do. They're just a tiny bit suppressed because they're just lost in this instrument noise floor. So that implies that having nearly 48 dB attenuation in my dummy loudspeaker is too much. A well-performing amplifier can't have its signal to noise ratio measured with the attenuator in place. Now, of course, we can always just do what I've done here and plug it in directly to the speaker, but that means I can't measure the signal to noise ratio at high levels, only at low levels like 0 dB, like I'm doing here. So just as a final thing, let me show you that we can actually remove this minus 30. So, you know, it'd be helpful if the yellow, the attenuated signal, were as though there were no attenuation. So at the moment our attenuation is minus 38.11 because it's cooling down a little bit finally. And so I can dial that in and we can see that the signal moves. And yeah, so the noise floor apparently moves, but it hasn't actually done so. It's just, of course, added 38.1 to it and moved everything up the scale a bit. But if we look on the left hand side now, we've got left peak dB volts 0. So our attenuated signal is now measuring this. Let me turn the right channel off because we don't need it anymore. So our attenuated channel is now being computed so that we can actually treat it as though it were the loudspeaker. If we look up here, we've got 0 dB volts, which is our output from our amplifier. We've got, that means 123 milliwatts into an 8.1 ohm load. Total harmonic distortion, minus 70.59. Our peak to peak left-hand voltage is 999.4. Well, that's just a rounding issue because it could be 0. We've got our full dynamic range because we've got our amplifier set to 0. So there's lots of good things about having this attenuation there. Okay, let's try and sum up then. So it's pretty usable as a general purpose load, 4 ohms, 8 ohms, plenty of power, and for short periods it's absolutely fine for testing as well. However, it does heat up too much to use for soak testing, where it would have to absorb hundreds of watts for several hours. So we could solve that potentially with bigger heat sinks, more ventilation, and potentially also adding some fans in. Now, next problem is attenuation versus impedance change. So you change the impedance, you change the attenuation, and it's awkward, it's not impossible, but we should try and overcome that if we can in a circuit redesign. What else? We've got too much attenuation, so almost 40 dBs of attenuation means that we're not really getting signal to noise ratios. If the amplifier is good, measuring its signal to noise ratio is going to be very, very tricky indeed. So again, that's about circuit design. We can modify the attenuation in our circuit and deal with that, hopefully. Yep. Okay, so here we go. Here's our redesign, and hopefully this is going to solve all of our problems. So first up, let's have a look at these resistor chains. So I'm aiming for about a 20 dB attenuation, 20 dBV attenuation. So we can see that I've changed this main chain from being 4 ohms and 0.1 ohms, and I've changed it to 3.6 ohms, which I've had to make up out of 1.8 ohm resistors because I just can't get 3.6 ohms. They're just out of stock everywhere. So two 1.8 ohm 50 watt resistors making up a 3.6 ohm 100 watt resistor. And then we've got a 0.82 ohm, so 820 milliohms, and that's our kind of sense resistor, if you like. And then we've got another 3.6 ohms at the bottom, and that makes 8.02 ohms, which is pretty much on the money, and is actually better than the current build. Now, if I take the attenuation factor on there, you treat that as a voltage divider, we get 20 log 0.82, which is the sense resistor, divided by 8.02, which is the total resistance of the whole chain, and we find that we've got minus 19.81 dB volts. So pretty much the 20 that I was looking for. I'm kind of suspecting with other inaccuracies in these resistors, the tolerances, that I might be pretty close to the 20. So how have I made it so that when I switch to 4 ohms, it doesn't change? Well, what I've done, instead of paralleling each of the resistors, I've paralleled the whole lot. So I've created an 8 ohm resistor by putting two 4 ohms in parallel, and these are just ones I'm scrounging back out the old design. So I'm going to take two 4 ohms, put them in series, that makes an 8 ohm, and I can switch that in parallel with the 8 ohms that I've already got, and that will make a 4 ohm resistor. However, the ratio of the voltage divider used for attenuation doesn't change at all. At no point is there a single change to that. All that happens is the current splits, half goes down through this 8 ohms on the left hand side and half goes down through the other 8 ohms, just as you'd hope. So that's really good news. Over on the right hand side, I've replaced the single BNC connector that I'm using for the monitoring port with a pair, and that's because it's actually a differential signal, and I wanted to make that absolutely clear on the front end here. So we can see that we've got a differential plus, differential minus, and there's a common as well going across to, in this case, the analyzer, but it could be something else. So that's pretty good. We've got the attenuation we want. I've had to replace the 4 ohm resistors on this main chain with 3.6 ohms, and that's because I've increased the sense resistor so much, and I've also had to, of course, increase the wattage of that resistor. Thermal performance, and have I managed to improve that? Well, I think I will have done. So first of all, the heatsink's doubled in size. I'm using a 0.6 Kelvin watt, so that's its natural sort of heat dissipation or heat resistance without a fan or anything like that. But I'm going to mount that vertically in a perforated case, so the top and the bottom will be completely perforated, 5mm holes every 8mm. On kind of a grid type pattern, and that should give loads of convective airflow through these. In actual fact, then our Kelvin watt resistance really drops through the floor at that point. Now, perforated top and bottom, that's great, but still for soak testing I think we need more airflow. So what I'm planning to do is to put two 150mm fans in the bottom, on that perforated bottom, blowing air up through these heat sinks and out of the top. I'm putting them on the bottom because it's cooler down there basically, and it's better to move cool air through your fans than hot air. All of the resistors in this divider chain, they're all 50 parts per million per degree C, and they're all from the same manufacturer. They're all the same case style. They're all wire wound chassis mount in the same series. So that's about as good as I can get without spending silly money on resistors. That's about as good as I can get in terms of thermally matching these. So I'm hoping for much better performance thermally than previously. And that will be helped by the better ventilation and things like that as well. So I think we've pretty much ticked off our list of things that we want to improve. We've actually improved the impedance matching slightly. We've improved the attenuation a little bit. We've improved the total temperature that it's going to reach. We've set up some facility for soak testing. We've hopefully improved the thermal stability, and yeah, everything that we needed to do, I think we've actually made an improvement on. So next video I'll put this together and we'll just see whether it works. I really think it's going to be significantly better. And I guess that brings us to an end. I think this video hopefully illustrated that even though a dummy loafer, let's say a loudspeaker, is fundamentally simple, there are some hidden little problems if you want to use it for measuring the performance of high quality amplifiers and things like that. Still, I hope you enjoyed it. If you did, don't forget, give it a thumbs up. Of course, subscribe if you haven't already done so, and feel free to leave some comments down below. I hope to get the next video out pretty quickly. I'm just waiting for the aluminium sheeting and the additional heat seeking to arrive, and that'll be it. I'll pop it together.